So we've built a telescope to catch the light coming down from the sky. If necessary, we've gone above the atmosphere to catch the kind of light that we want to. But now what we have to do is to record the information that we're seeing using some kind of detector. Now, a detector does four things for us. Firstly, it makes an objective record of what it is that we're seeing. The second thing is it allows us to digitize the information. Pretty pictures are all very nice, but as scientists we want numbers. The third thing is that it allows us to integrate, that is to take long exposures to gradually add up more and more light so we can see fainter and fainter objects. The final thing is perhaps the most important. With detectors of various kinds, we can detect kinds of light that we cannot see with our eyes, infrared, X-rays, radio, etc. And so we discover things about the universe we otherwise would not know existed. Let me show you some examples. So this first example is a giant radio galaxy. It's the radio galaxy Hercules A. So the image you're looking at, the purple colour is a map of the radio emission as measured with the Very Large Array in New Mexico. It's superimposed on a regular visible light picture so you can see the parent galaxy. So what you see in that purple emission is two twin jets of radio plasma stretching out an enormous distance into space. And we think these have been squirted out of a black hole in the very centre of that galaxy. So extraordinarily interesting. To see that radio emission, we need an antenna and a radio receiver. Otherwise, we would never have known that such extraordinary things existed. So this next example is one you've seen before. This is hot gas from the cluster of galaxies Abell 1689. So in this image you're looking at, the purple colour in this case is X-ray emission measured by the Chandra Space Observatory, and it's superimposed again on a regular visible light image taken with the Hubble Space Telescope, where you can see the galaxies in the cluster of galaxies. So what the X-ray emission is showing us is smooth emission from very hot gas. It has to be tens of millions of degrees, almost 100 million degrees, to radiate those X-rays. So once again, we need a special kind of detector. We need some substance that detects X-rays, otherwise we would not have known that gas was there. As well as being very fascinating, it's very important because from the temperature and the brightness of that X-ray gas, we can weigh the dark matter in that cluster, and it turns out to be 99% of the mass of that cluster. So this final example is the Hubble Ultra Deep Field, a very deep picture taken by the Hubble Space Telescope. This image shows the importance both of integration and of observing at different wavelengths. So the faint, tiny smudges that are circled in the image you're looking at are showing you the locations of some of the most distant galaxies we know of. Now, in order to detect those incredibly faint smudges, the Hubble Space Telescope stared at the same patch of sky for 4 days non-stop, a total exposure of 173,000 seconds. It just kept adding up more and more and more light to see extremely faint things. So that's how we can see those very, very distant galaxies. But also, as you'll be hearing later this week, those distant galaxies are redshifted. Their light is mostly emitted in the infrared rather than as visible light. So to measure that best, we need infrared detectors as well as visible light detectors. So there you have some science examples, the kind of science we can do with detectors of various different kinds. What we want to do this week is to understand how those detectors work. How do we actually achieve this? To do that, we need to look at how light interacts with matter and then how we assemble devices into instruments we can actually use. So that's our task this week. But before we do that, Catherine is going to tell you a bit more about those extremely distant galaxies.